Hello, in this video we continue our unit on chemical bonding. In the previous video we talked about VSEPR theory and molecular geometry. In this short video I'd like to talk about molecular polarity. What does it mean to say that something is polar, a bond or a molecule or anything for that matter? Well, polar simply means that it has a permanent separation of charge. So if I consider this big turquoise blob to be a molecule of some sort, if one end of the bond has a slight positive charge and the other has a permanent slight negative charge, then I'm going to say that this molecule is polar. We would say that it has a dipole moment, and this separation of charge represents a dipole. So, what criteria must be met for a molecule to be polar? Well, the molecular geometry must be asymmetric so that the bond dipoles do not cancel out. Let me give an example of that on the next slide. If we consider carbon dioxide, I draw a Lewis structure, I assign the molecular geometry, and I see that it is a linear geometry, and the bond angle, of course, is 180 degrees. Each of the carbon-oxygen bonds is highly polar. There is a pretty substantial electronegativity difference between the carbon and oxygen, so that each oxygen has a permanent partial negative charge, and the carbon has a permanent positive charge on it, partial positive charge. But keeping in mind the high symmetry of the molecule due to its linear geometry, the two bond dipoles, represented by the green arrows below, cancel each other out. Consider them to be vectors that add up to zero. Therefore, the molecule overall is nonpolar. On the other hand, if I consider a molecule like water, I draw the Lewis structure, and I see I have a bent geometry with a bond angle of 109.5 degrees approximately. I still have two very, very highly polar covalent bonds. There's a large electronegativity difference between the oxygen and the hydrogen, giving me a substantial partial negative charge on the oxygen and a substantial partial positive charge on the hydrogen. But now, because of the asymmetric geometry, the fact that it's bent, those oxygen-hydrogen bond dipoles, again represented by the green arrows, do not cancel out. They add up to an overall molecular dipole, indicated by the green arrow to the right, and as a result, water is polar. Notice that the arrows used to represent the dipoles have the arrowhead pointing towards the partial negative charge and the cross at the opposite end to represent the partial positive charge. So now let's systematically go through the molecular geometries we learned about in the previous video and determine which ones are highly symmetric and therefore result in nonpolar geometries, which ones are highly asymmetric and result in polar geometries. So, assuming that all AB bonds are polar and equivalent, here are the nonpolar molecular geometries that are due to the high symmetry of the molecule resulting in cancellation of the bond dipoles. AB2 linear, AB3 trigonal planar, AB4 tetrahedral, AB5 trigonal bipyramidal, AB2E2 linear, AB6 octahedral, and AB4E2 square planar. What you'll notice is that nearly all of these lack lone pairs on the central atom. And for most of these, not having a lone pair on the central atom means that the bonds will be so symmetrically arranged that the bond dipoles will cancel out. Those that do have lone pairs, namely AB2E3 linear and AB4E2 square planar, are still sufficiently symmetrical so that the bond dipoles add up to zero. And you can go back and look in your notes and convince yourself of that. On the other hand, the polar molecular geometries, the ones that have highly asymmetrical geometries in which the bond dipoles do not cancel out, include AB2E bent, AB2E2 bent, AB3E trigonal pyramidal, AB4E seesaw, AB3E2 T-shaped, AB5E square pyramidal. And note that all of these have one or more lone pairs on the central atom that push the bonds out of symmetry and therefore result in polar molecules. Let's do some examples. For each of these, we're going to use VSEPR theory to predict the molecular geometry, including bond angles, and state whether the molecule is polar or nonpolar. I've already drawn the Lewis structures for you. If you want to pause the video here and try them yourself, you are more than welcome to. Arsenic trifluoride is an AB3E type molecule, which is trigonal pyramidal. I'll just abbreviate there, with bond angles of 109.5 degrees. That lone pair makes the central atom asymmetric, so this will be a polar molecule. Carbon disulfide is an AB2 type molecule, which has a linear geometry highly symmetric, bond angle of 180 degrees, highly symmetrical, so nonpolar. Sulfur trioxide, SO3, is an AB3 type molecule, which therefore is trigonal planar with bond angles of 120 degrees, highly symmetrical, so nonpolar. Germanium tetrabromide is an AB4 type molecule, which has a tetrahedral geometry with bond angles of 109.5 degrees. The high symmetry means the bond dipoles cancel each other out. This is a nonpolar molecule. For our final examples, xenon dichloride we see is an AB2E3 type molecule and is therefore linear. Note that despite the fact that it has lone pairs on the central atom, the high symmetry, namely 180 degree bond angle, means that it will be nonpolar. Iodine tribromide is an AB3E2 molecule, which therefore is T-shaped with 90 degree bond angles. The bond dipoles do not cancel out, so it is a polar molecule. Selenium tetrafluoride is an AB4E type molecule, which is seesaw geometry. It has 90 degree and 120 degree angles. The bond dipoles do not cancel out, so it is a polar molecule. And finally, phosphorus pentachloride, an AB5 molecule, has trigonal bipyramidal geometry with bond angles of 90 degrees and 120 degrees. No lone pairs on the central atom, high symmetry, so it is non-polar. And that is molecular polarity.